Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? Lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around. An incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronic stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead-acid, can't be recycled together. At smaller collection points, like those in cities, workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries, because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals. For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace, where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials. Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines
equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting, and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material. Stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact, old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning, the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term. A gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila, a new product appears. The packaging for your favorite smoothie or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper, or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. Did you know that railroad tracks can actually bend like noodles? Yet in an instant, they become tougher than rock. Every year, over 15 million tons of steel are used to build these tracks. But how do we transform raw iron ore into rails that can withstand the weight of thousands of tons? Stick around to discover how cutting-edge technology and precision engineering are revolutionizing infrastructure. The process of manufacturing railroad tracks is a fascinating blend of advanced technology and heavy machinery. But it all begins with iron ore. This ore is mined either in open pits or underground. Open pit mining is used when deposits are near the surface, employing massive excavators and drilling machines. For deeper ore deposits, underground mines are excavated. Once the ore is extracted, it is crushed and refined through several stages to separate the iron and remove impurities. The enrichment process involves crushing, grinding, and either magnetic or flotation separation, which produces a concentrate with a high iron content. To create a strong and flexible alloy, carbon is added to the iron ore. This carbon typically comes from coking coal, which undergoes high-temperature processing. Other elements like chromium, manganese, nickel, or molybdenum are also added to the steel to enhance its strength and other critical properties. Every year, more than 15 million tons of steel are used worldwide for railway tracks. This represents a significant portion of global steel production, and demand continues to grow due to infrastructure expansion and the need to replace worn-out tracks. After extraction and initial processing, the raw materials are transported to steel mills. Rail and maritime transport are commonly used, especially for long distances, since ore is often mined in remote areas. Thus, steel production for rails involves combining various materials sourced from different parts of the world, with the extraction and processing stages relying on complex machinery and a multi-step refining process. The production of railway tracks begins in the steelmaking facility, where iron ore and other components are melted in specialized electric or blast furnaces to create molten steel. Carbon and alloying elements are then added to the steel to enhance its strength. Once the desired composition is achieved, the metal is maintained at a high temperature to ensure uniformity. The molten steel is poured into large molds, forming slabs, rectangular blocks of steel that will eventually be shaped into rails. After cooling, the slabs are transported to the rolling mill for further processing. A rolling mill is a massive machine that shapes steel slabs into the desired form and size for rails. The slabs pass through a series of rollers, which gradually reduce their thickness and form the railhead, web, and base. The rails are rolled at temperatures exceeding 1,832 degrees Fahrenheit, making the metal more pliable. To increase the hardness and wear resistance of the rails, a heat treatment process is applied. The rails pass through cooling chambers, where the temperature is gradually reduced, minimizing internal stress in the metal. Typically, 1 foot of rail weighs about 45 to 55 pounds, meaning a standard rail weighs approximately 3,858 pounds. A large steel mill can produce around 3,500 feet of rails per shift, roughly 10,000 feet per day. Once the rails are finished, they undergo thorough inspections for defects such as cracks, surface irregularities, or other damage. Specialized ultrasonic and X-ray techniques are used to ensure quality. After inspection, the rails are cut to standard lengths of approximately 1,000 inches, and their ends are machined for easier connection during installation. Once manufactured, the rails are transported to construction or repair sites. Trains specially designed for carrying long rails are typically used for this purpose. Freight cars secure the rails tightly to prevent any movement during transit. Laying railroad tracks is a complex process that requires the use of specialized machinery. First, the ballast, which serves as the foundation for the ties and rails, is leveled and compacted along the railway bed. This ballast is crucial for the stability of the tracks and for proper drainage. Ballast spreaders evenly distribute the crushed stone, creating a stable layer on which the ties and rails will be laid. Automatic tie-laying machines then place wooden or concrete ties on the prepared ballast base, ensuring they are spaced precisely. These machines are equipped with sensors to maintain an exact distance between the ties, which is essential for the stability of the future track. Railroad rails can last up to 30 years or more, depending on the volume of traffic and environmental conditions. However, on high-traffic routes, such as those used for freight trains, rails may wear out more quickly and require replacement every 10 to 15 years. Next, the rail laying machines take over. And oh my goodness, what a mesmerizing sight it is. When we think of rails, we usually picture something as rigid as stone. Yet during the laying process, they seem to bend under the influence of the machines, almost like rubber bands. In reality, this is due to the immense forces acting on them. When rails are first rolled out, they're heated to extremely high temperatures to make the steel more malleable and easier to shape. During installation, rails are sometimes reheated to prevent future thermal expansion, which gives them that seemingly softer, more pliable appearance. Specialized machines carefully lift, align, and position these long sections of rail as though they're weightless and not the solid, unyielding steel we know them to be. It's all thanks to precise manipulation and the illusion of flexibility, which cleverly conceals the incredible strength of the steel. This is one of those fascinating railway magic tricks, where raw power and advanced technology combine to create a spectacle that's as captivating as it is impressive. Workers then join the rails using specialized bolted or welded joints. Thermite welding or electric welding equipment is employed to create a seamless rail line, ensuring a smooth ride for trains. It's remarkable how much effort goes into making it possible for me to visit my favorite grandma, or for any office worker to commute to their job. To secure the rails to the ties, special fasteners are used to clamp them firmly in place. This ensures stability and prevents the rails from shifting under the weight of passing trains. Rails have the ability to freely expand and contract by a few millimeters for every 10 yards, depending on the temperature. As a result, when laying tracks, engineers take average annual temperatures into account. In some cases, the rails are even heated to a specific temperature during installation to minimize the effects of thermal expansion. Automatic fastening machines quickly install bolts or clips to connect the rails to the ties, significantly speeding up the process. Once the rails and ties are in place, specialized machines align the track by lifting or lowering the ties and adjusting the ballast beneath them. Thanks to laser sensors and computer control, these machines ensure precise track alignment, which is critical for safety. Other machines tamp the ballast, crushed stone, around the ties, providing a solid foundation. This reduces the risk of track shifting and enhances its resistance to vibrations. These machines are equipped with special tamping arms that dig deep into the ballast and compact it firmly around the ties. Rails are often made using a significant percentage of recycled steel, as steel retains its properties well during reuse. This helps reduce the need for new